To understand how neural networks actually learn, we have to look past the hype and focus on the math. As Elon Musk points out, machine learning is essentially 99% dot products. To see why, we need to start with the most basic building block of deep learning, a single neuron. You can think of a single neuron as a complete, self-contained black box that takes in data and produces a concrete output. Before any data can enter this box, whether it is audio, text, or video, it must be translated. Every digital input has to be converted into an array of numbers. Take this photograph of a dog, for example. We can process this image and extract its pixel data to create a fixed-length, one-dimensional sequence of numbers. That numeric sequence serves as our input vector. The neuron processes that sequence to make a single binary decision, producing a 1 if it detects a dog or a 0 if it does not. At this foundational level, the network acts as a mathematical translator, stripping away visual context to produce a simple binary choice based entirely on the numeric input vector. A neuron relies on weights, bias, and an activation function. First, the neuron pairs each input element with a dedicated weight. It multiplies every input by its corresponding weight, sums the results, and adds the bias term to create a single linear combination. In linear algebra, this operation of matching equal-length vectors, multiplying their pairs, and summing the total is called a dot product. We use this specific calculation because it is the simplest possible way to guarantee that every single piece of data in the input vector is factored into the final sum. It is also incredibly fast to execute. Modern processors, especially graphical processing units, are engineered to run these specific additions and multiplications in parallel across massive datasets. The perceived intelligence of AI is driven by the brute force speed of hardware executing billions of these rudimentary dot products. Combining data only in straight, linear ways is insufficient for capturing the nuance of complex real-world data points. This is where the activation function comes in. It takes the linear sum produced by the dot products and applies a specific formula to it, injecting necessary nonlinearity into the neuron's final output. This data visualization shows exactly why that flexibility matters. On the left, a rigid linear boundary fails to cleanly separate our data points. On the right, a nonlinear boundary bends and curves, successfully grouping the specific target categories. While the neuron will constantly adjust its weights and bias to reach the right answer, the activation function operates under a strict rule. Its mathematical formula is permanently locked at the time of creation and never changes during the learning process. Without that rigid, nonlinear switch, the neuron would be trapped making overly simplistic assumptions, unable to draw complex boundaries between concepts like dog and not dog. When a neuron is first created, its weights and biases are completely random. When we feed it an input vector for the first time, its output guess will inevitably be incorrect. To fix this, the network calculates the error. This is the exact, quantifiable difference between the neuron's incorrect guess and the expected answer provided during training. This diagram represents a loss function, mapping errors to show how badly weights are performing. High elevations mean high error. The bottom is our goal. To navigate, the network uses gradients as a compass, determining the fastest path to minimal error. This creates a continuous optimization loop. The gradient directly informs the system exactly how to continuously tweak the internal numbers of the weights and bias slots until the neuron's output aligns with reality. Machine learning is entirely devoid of cognitive understanding. It is an automated, gradient-driven feedback loop relentlessly seeking the mathematical floor of an error graph. A single neuron executing this optimization loop is mathematically sound, but its capacity is limited. One neuron alone cannot map arbitrarily complex concepts on its own. To solve difficult problems, we scale up. By layering billions of interconnected neurons in a sequential web, we create a complete deep neural network. Scaling this simple mathematical engine to astronomical, multi-layered proportions allows the network to handle arbitrarily complex tasks. Ultimately, a massive deep neural network is just a physical sequence of layered neurons. Training that network is just the computational hunt for the optimal combination of weights and biases across every single layer in order to reduce the loss function. And the gradient remains the essential navigational tool, dictating exactly how those millions of values must change to successfully identify a pattern. The capability of a deep learning system is entirely predictable. It is the triumph of massive parallel processing, fundamental calculus, and the humble dot product.